In December of 2024, Google's quantum computing division published a result that quietly rewrote what a lot of physicists thought was possible. They called the chip Willow. It has 105 qubits. It lives inside a refrigerator colder than deep space. And on paper, it looks like a small silicon wafer no bigger than a coin. But the moment you understand what that wafer actually did, you start to understand why some of the people who built it walked away from their own results asking questions that sound less like engineering and more like philosophy. This is not a story about a machine that talked to God. No machine did that. This is a story about a machine that ran a very hard math problem in 5 minutes, about the honest and genuinely strange interpretation some physicists have offered to explain how it did that, and about a much older question, whether the universe itself looks built. That this machine has nothing to do with proving, but that its existence makes impossible to ignore. Let's start with the part that is not in dispute, because it's already strange enough on its own. Every computer you have ever touched, your phone, your laptop, the servers this video is streaming from, runs on bits. A bit is either a 0 or a 1, on or off, and nothing in between. Your entire digital life. Every text message, every photo, every terrible group chat is ultimately just an enormous, fast-moving string of those two symbols. That architecture has taken humanity from vacuum tubes to smartphones in under a century, and it is genuinely one of the great achievements of the species. But it has a ceiling. There are problems that grow so explosively complicated that no amount of clever engineering, no faster chip, no bigger data center, will ever bring them within reach of a classical computer. The number of possibilities involved simply outpaces the number of atoms available to compute them. Quantum computers were built to go around that wall instead of through it. Willow doesn't use bits. It uses qubits, and a qubit does something a normal bit structurally cannot. It holds two states at once, a haze of 0 and 1 simultaneously, a condition physicists call superposition. It doesn't resolve into a single definite value until it's measured. Pair that with a second and even stranger property called entanglement, where two qubits become linked so that measuring one instantly tells you something about the other, no matter how far apart they are, and you get a machine that isn't just calculating faster. It's exploring an enormous landscape of possible answers all at once, letting the wrong ones cancel each other out through interference until the right one is left standing. Einstein famously distrusted entanglement so much he called it spooky action at a distance, and spent years trying to find a loophole that would make it not true. There isn't one. It has since been confirmed by decades of experiments, including ones that won the 2022 Nobel Prize in Physics. So what did Willow actually do with all this? Google gave it a benchmark task specifically designed to be brutal for a classical computer, a random circuit sampling problem, essentially asking the chip to simulate the statistical output of its own impossibly complex quantum circuitry. Willow finished it in under 5 minutes. Google's own estimate was that one of the fastest supercomputers on Earth today would need something on the order of 10 septillion years to do the same calculation the conventional way, a number so far past the age of the universe that comparing them is almost a category error. That gap between 5 minutes and a number with 25 zeros in it is the entire reason this chip made headlines. It isn't a difference of degree. It's a difference of kind. Here's where the story stops being pure engineering and starts drifting towards something stranger. When Google's team examined what Willow had actually done during that computation, they ran into something uncomfortable. By some ways accounting the information involved, the sheer scale of the calculation seemed larger than what the particles in our observable universe could plausibly be tracking, if you assume the computation is happening only in the universe we can see. That observation is genuinely part of the discussion around random circuit sampling, and it's the reason Hartmut Neven, who leads Google Quantum AI, has publicly floated an explanation that sounds like science fiction, that the computation might, in some sense, be distributed across the many parallel branches of reality predicted by the many worlds interpretation of quantum mechanics. It's worth pausing on where that idea actually comes from, because it did not appear out of nowhere to sell a headline. The many worlds interpretation was proposed by the physicist Hugh Everett in 1957 as one serious answer to one of the oldest unsolved puzzles in physics. What actually happens when a quantum system is measured and its haze of possibilities collapses into one outcome? Everett's answer was that nothing collapses at all. Instead, reality itself branches, and every possible outcome plays out, each in its own separate, mutually invisible universe. The Oxford physicist David Deutsch, one of the intellectual founders of quantum computing itself, has spent decades arguing that quantum computers are actually our best empirical evidence that those other branches are real, because when a machine performs a calculation too large to fit inside the resources of a single universe, something has to be doing that work somewhere. None of this is settled science. Many worlds is one interpretation among several serious contenders. There's also the Copenhagen interpretation, pilot wave theory, objective collapse models, and others, and physicists disagree, sometimes sharply, about which one, if any, correctly describes reality. What's true is that a machine like Willow forces that disagreement out of the seminar room and into a demonstration you can actually watch run in under 5 minutes. That's genuinely new. It doesn't resolve the debate. It sharpens it. And it's worth saying, in the interest of giving you the full picture rather than only the exciting half of it, that plenty of physicists working in this exact field pushed back hard on the parallel universes did the computing framing when it went public. The computer scientist Scott Aaronson, one of the most prominent voices in quantum computing theory, has argued for years that random circuit sampling results like Willow's don't actually require invoking other universes at all. The exponential complexity involved is a known, well-understood feature of how quantum amplitudes behave mathematically, whether or not you believe those amplitudes correspond to literal parallel worlds. In other words, you can fully explain what Willow did using nothing but the standard, uncontroversial mathematics of quantum mechanics. The many-worlds language is an interpretation laid on top of that math, not a conclusion forced by the experiment itself. Nevin's comments reflect one legitimate, well-credentialed reading of a genuinely strange result. They are not the only reading, and they are certainly not a scientific consensus. That distinction matters more than almost anything else in this story, because it's exactly the kind of nuance that gets flattened the moment a headline needs to fit inside a thumbnail. Now here's the second thread of this story, and it's the one that quietly does the heaviest lifting. Quantum information is famously, almost comically fragile. A stray vibration, a passing cosmic ray, a single misplaced photon, and the delicate superposition a qubit is holding collapses into garbage. For years, this fragility looked like a dead end for the entire field, a beautiful theoretical idea that could never survive contact with a messy physical laboratory. Then, in 1995, the physicist Peter Shor showed that fragility didn't have to be fatal. He proved that you could encode quantum information redundantly across multiple physical qubits in a way that let you detect and correct errors without ever directly measuring, and thereby destroying the fragile quantum state itself. This was the birth of quantum error correction, and it is a single idea that makes real quantum computing possible at all. Willow's headline scientific result, published in the journal Nature, is built directly on this idea, and it is genuinely remarkable on its own terms. For decades, adding more physical qubits to a quantum system made errors worse, because more qubits meant more opportunities for something to go wrong. Willow was the first system to demonstrably cross what's called the error correction threshold, the point where adding more physical qubits to a logical, error-corrected qubit actually makes the system more reliable, not less. That is the opposite of how every fragile physical system is supposed to behave as it scales up, and it's the reason physicists working outside Google's own lab treated this result as a legitimate milestone rather than corporate hype. Here's where things get genuinely philosophically interesting, and where I want to be careful, because this is a part where reference videos on this topic tend to blur real physics with wishful thinking. There's a real and active area of theoretical physics exploring whether the structure of space-time itself behaves like an error-correcting code. This isn't numerology. It comes out of work on the holographic principle, the idea, well supported by decades of research into black hole physics, that all the information contained within a three-dimensional region of space can in principle be encoded on its two-dimensional boundary, the way a hologram stores a 3D image on a flat surface. Physicists including Ahmed Almhiri, Shidong, Daniel Harlow, and John Preskill have shown, using the AD/CFT correspondence, a mathematical duality relating a theory of gravity in a bulk space to a quantum theory on its boundary, that this holographic encoding follows mathematical patterns strikingly similar to quantum error-correcting codes. That is a real, published, actively researched result. It is also, importantly, a mathematical analogy operated within a specific theoretical framework, not direct experimental proof that our actual universe is protected, the way an engineer protects a message. Serious physicists working in this space describe it as a fascinating structural resemblance worth investigating, not as settled evidence of a designer. It is genuinely interesting that the same mathematical family showing up in Shor's 1995 error-correcting codes also shows up in theoretical descriptions of how information might be organized at the deepest levels of space-time. Whether that resemblance means something profound about the nature of reality, or whether the case of same elegant mathematics simply being useful in more than one place. The way calculus shows up in both orbital mechanics and economics without either field borrowing from the other is an open and genuinely contested question. I'd rather tell you that honestly than pretend the answer's obvious. So let's talk about the other half of this puzzle, the part that has nothing to do with quantum computers at all, and everything to do with why the universe looks, to a lot of very careful scientists, suspiciously well-suited to producing anything like us. The cosmological constant, the energy density built into empty space itself, the number that determines whether the universe expands forever or eventually collapses, sits at a value so precisely balanced that physicists routinely describe it as one of the strangest numbers in all of science, shifted by an almost unimaginably small fraction in either direction, and you get a universe that either flies apart before galaxies can form or collapses back on itself before stars ever ignite. There's a smallest meaningful unit of length, the Planck length, below which our current physics simply stops making sense. There's a universal speed limit that nothing carrying information can exceed. And there's a famous case of stellar carbon synthesis. In the 1950s, the astronomer Fred Hoyle worked out that for carbon, the element every living thing on Earth is built from, to exist in the quantities it does, carbon nuclei needed to fuse inside stars at one very specific resonance energy. No one had found that resonance yet. Hoyle predicted it had to exist purely from the logic that we are here, made of carbon, to ask the question. Experimentalists went looking. It was there, essentially exactly where his reasoning said it would be. It's also worth pointing out just how many of the universe's basic dials seem to line up this way at once. Because a single coincidence is a curiosity, but cluster them is what actually makes physicists uneasy. The relative strengths of the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, sit in a ratio that, if nudged even slightly, would either prevent atoms from forming stable structures or cause stars to burn out before life-bearing planets could ever settle into orbit around them. The precise amount of matter generated relative to antimatter in the earliest moments after the Big Bang left just enough leftover ordinary matter to build everything from hydrogen to galaxies, instead of a universe that annihilated itself into pure light within its first second. None of these numbers were derived from first principles by any theory we currently have. They're measured, plugged in, and then quietly noted as suspiciously convenient. That's the observation fueling this whole conversation, and it deserves to be taken seriously precisely because it comes from careful measurement, not speculation. These are genuinely strange facts, and I don't think it does anyone favors to pretend they aren't. But it's worth being just as honest about the leading scientific explanation for them as I've tried to be about everything else here. The most widely discussed answer among physicists isn't a designer. It's the anthropic principle, often paired with some version of a multiverse. If there are many universes or many regions of a single vast universe, each with different physical constants set essentially at random, then almost all of them would be sterile and lifeless. We would only ever find ourselves in one of the rare universes where the constants happen to allow stars chemistry and observers capable of noticing the constants in the first place. On this view, fine-tuning isn't a signature left by a builder. It's a selection effect, the only kind of universe anyone could ever be around to be surprised by. This is a legitimate, actively defended position in cosmology, championed by physicists like Steven Weinberg and Alan Guth, among many others. It doesn't require inventing a multiverse out of nothing to solve the fine-tuning problem. It emerges naturally from serious cosmological models like eternal inflation. It's also, to be fair, not universally accepted either. Some physicists find appeals to unobservable other universes philosophically unsatisfying and prefer to leave fine-tuning as an open mystery rather than explain away with unfalsifiable machinery. So where does that leave us? Nowhere near a machine printing out the name of a creator, which is worth saying plainly. No experiment, quantum or otherwise, has ever done that, and any framing that suggests Willow was literally asked, "Who built the universe?" and returned a coded answer is dramatizing something that didn't happen. What Willow actually did is much more modest and, honestly, more interesting than that framing gives it credit for. It's a working demonstration that quantum mechanics, a theory built on ideas so counterintuitive that its own founder spent decades arguing about what it even means, can be harnessed to do real computational work. Work so far beyond classical reach that it forces serious scientists to publicly entertain interpretations, like many worlds, that sound like they belong in a novel, and its architecture happens to lean on the same mathematical toolkit, error-correcting codes, that shows up independently and for entirely different reasons in some of our best current theories about how space-time itself might be structured. None of that proves design. None of it proves the opposite either. What it does is put three genuinely open questions back on the table at the same time, in a way that's hard to ignore, whether there's only one universe or many, whether the strange mathematical order we keep finding in nature, from carbon resonances to holographic error correction, is evidence of something, or just what elegant mathematics inevitably looks like when a universe is complex enough to support beings capable of noticing it, and whether "why does anything work at all" is a question science will ever be equipped to answer, or one that will always sit just past the edge of what a machine, however powerful, can tell us. If I had to leave you with anything honest, it's this: Willow didn't answer the oldest question humans have ever asked, but it's a genuinely new kind of instrument, aimed for the first time at a layer of reality where physics starts to look less like objects bumping into each other and more like information being processed. And every time in history that we built a new instrument and pointed it at something we couldn't see before, a telescope, a particle accelerator, a gravitational wave detector, the universe has turned out to be stranger, not simpler, than we expected going in. Willow is very likely no exception. Google has already said publicly that this chip is an early step, not an endpoint, on the way to far more capable machines. Whatever those machines eventually let us glimpse, I don't think anyone alive right now knows for certain. That uncertainty isn't a failure of the story. It might be the most honest place a story could possibly end.